In this video, I'd like to look at the two standard deviation functions that Excel offers and sort of go behind the scenes and see what each calculation involves and what the difference between them is. So I started off, I just had some data, and it doesn't matter what the data is. I have 100 points. I generated it, quasi-randomly. Okay. So now, anyway, I have some data and I would like to do some statistical measures on it, specifically the standard deviation, which tells us how, is a measure of how spread out the data is. So we start off with the idea of a deviation, which is how far are you from the average or mean. So over here in F2, I'm taking the average using Excel's average function for A2 to A:A101. So that is the average of my data or the mean of my data. And then I'm coming over here and just grabbing the definition of the deviation, which is how far are we from average. And so it is, I'm taking the data point A2 minus F$2. And then as I drag this formula down, the A2 becomes A3, so I'm visiting all the data points, but with the $sign under the F, it stays F2, it stays the mean. So I have the deviations, they go all the way down. Now the deviations, some of them are above average, some of them are below average. That's the definition of average, that there will be deviations above and deviations below. And so we can't use the average deviation to measure the spread because that would just be 0. So the next thing we do is get the deviations to get positive deviations by squaring. So, and then we're going to undo that later on by a square root, which will come at the end. So we are now squaring the deviations. And so that was B2 caret 2, which is, so we're squaring all these numbers. Okay. And when you square a number, they're positive, so we don't have the cancellation problem that we did with column B and column C. I know I generated the data, so I knew there were 100 points, but I used count to explicitly count them. Okay. And then I am adding up those square deviations. So I want to effectively take an average of the square deviation. So I'm adding them up and then I'm going to divide. The distinction comes in what I divide by. And then because I got there by squaring, I'm going to undo that in the end by taking the square root. Okay, but at this stage, I have summed the square deviations. So we found the deviations. They were some were positive, some were negative. We squared them. Now they're all the squares are positive. We've added them up. And if we were going just for a straight average of the square deviations, we would divide by the number of points, the n, and that's what was done here. And because you can see these numbers are pretty much the same, except for moving the decimal place 2 places because I had 100 points. But down here, I'm instead dividing by n minus 1. So that's part of the distinction between standard deviation P and standard deviation S that we want to look at. And then if these had some units, if they were, I don't know, distances or temperatures or what have you, if they had some kind of unit, then the problem with this over here is that those units would be square. So we want to undo that by taking the square root. So I take the square root here where I took divided by n, here we're divided by n, but in both cases, I took, there's the n minus 1, F3 was the count, and here I'm taking the square root of each consecutively. Okay, and then I'm comparing that to Excel's STDEV.P, the population standard deviation, and STDEV.S, the sample population, and we see that I'm getting like agreement to, what is that, 6, 7 decimal places here. So these are the same. So this is indeed the calculation that gives STDEV.P, and this with the n-1 is the definition that gives the STDEV.S. Okay, so this is my explanation. This is the population, so that imagines that this data is definitively the data set. And so we are going to deal with it as it is. And so take the average of the deviation squared and divide by n. Whereas the sample imagines that this is a data of, then it is a subset of all the possible data. And so then we have to imagine that more data would be coming. And that's this n-1 is a way of sort of dealing with that this isn't all the data, more could come, and we want to try to some extent work with what we have, but take into account that there is theoretically more coming. Okay, so the extreme differences, let's try to understand. So one says I have everything, and the other one says more is coming. And the extreme difference, the biggest difference will be when n is 1. So let's imagine there's just one data point, and I'll take the first one. So here's the standard deviation.P, the population of a single data point A2, and it's saying if that's all there is, there's no spread. Whereas the sample says if there is one point and others are coming, I know nothing about the spread, and so it's undefined. So that's what these two different definitions. I've also seen this one called the root mean square deviation. That's sort of defining what you do. You take the deviation, you square them, you take the mean of them. So root, and then you take the root of it. So root mean square deviation. Take the deviation, square it, take the mean, take the root. But the normal, what most people will call the standard deviation, divides by n-1. That's the sample version in Excel. They have the population and the sample version divides by n-1, trying to take into account what's coming next. That's what I wanted to show you here. Thanks for your attention.